Hello, everyone. I'm going to give you a quick example to show you the difference between our classical probability and the empirical probability. And I'm going to do that by showing you a quick simulation in R. So to begin with, let's say that we are going to roll a six-sided die. So I'm going to call our dice just the values 1 through 6. And then if I do this, you'll see that we have the values 1, 2, 3, 4, 5, and 6. Then I'm going to set an object that is n, which will be how many times we're going to roll that die. Now what we're going to do is we're actually going to roll the dice. So we're going to roll the die 10 times. We have a six-sided die, and we'll roll it 10 times. So I'm going to set this as rolls. We're going to sample dice 10 times with replace equals true, which just means that I can get the same value more than once. So now I will tell it to tell us what the outcome rolls are. Okay, so we rolled our die. The first roll, we got a 5. Second roll, we got a 2, 4, 1, 2, 5, 1, 3, 3, 1. So now what I'm going to do is I'm going to create a table to show our rolls. And you'll see that we got 1 3 times. We got 2 2 times, 3 2 times, 4 1 time, and 5 2 times. So now if I were to do the same thing, I'm going to turn it into the probability. I'm going to take table of rolls, and I'm going to divide that by how many rolls we did. So this means that according to our empirical probability, the probability that I would roll a 1 is 0.3. The probability of rolling a 2 is 0.2, probability of rolling a 3 is 0.2, probability of rolling a 4 is 0.1, and probability of rolling a 5 is 0.2. Now, we know that this diverges from our classical probability because our classical probability is just going to be 1 divided by 6, which would give us a probability of 0.1666 on and on and on. So what I'm going to do actually is I'm going to take that value and I'm going to round it to 3 decimal places. So we get a probability of 0.167. And you can see that this is not what we got when we actually rolled our dice. So let's say then that we take this to the next level. We're going to do the same thing, but this time we're going to roll 100 dice. So let's roll our dice 100 times. Put that in. And these are 100 dice rolls, 5, 2, 3, 5, 2, so on and so forth. So now if we create a table, you see that we got a 1 16 times. We got a 2 12 times. We got a 3 23 times, a 4 13 times. We got a 5 18 times, and a 6 18 times. So putting it again into our table, we have these probabilities. Now notice some of them are a bit closer, but still not really lining up with our 0.167. So now we're going to take it, because we're going to use the law of large numbers. So if I do a lot of dice rolls, however many dice rolls this is, what's going to happen? Okay, too big. Try that. Thinking. That's what this little stop sign here means. It means that it's calculating. So what it's doing is right now it is rolling the die 100 million times. Okay, so we have 100 million dice rolls. So now what we're going to do is we are going to create a table. I'm going to jump straight to the probability. Take a second. And you'll see that, look at our probabilities. They are 0.167, 0.167, 0.167, 0.167, 0.167, 0.167. So what happened? When we were in the small scale, rolling the die 10 times, 100 times, our empirical probability, which is the probability based on those actual dice rolls, were what we got because of those dice rolls, which diverged from the classical or theoretical probability. When we did many, many, many rolls, we started to come upon the law of large numbers. Our empirical probability approached our classical probability. So let's do one more example. Let's say in this case now what we're going to do is we're going to roll a 20-sided die. So I have a 20-sided die, and I'll go back to just rolling it 10 times. And I'm going to roll my 20-sided die 10 times. So I have a 12, a 1, a 12, a 20, a 15, a 20, a 2, a 1, a 2, 20, and a 17. So I'll create my table. I'll create my probabilities. Now remember, this is a D20, meaning that there are 20 faces to this die. And yet I only have a probability for 1, 2, 12, 15, 17, and 20, meaning that according to my empirical probability right now, the probability of getting a 3 or 4, 5, 6, 7, 8, 9, 10, or 11 is 0, right? And we know that's not true. And then if we were to quickly look at what should our probabilities be, this is the probability we should get for all of the dice rolls, 0.05. Probability of any specific roll on a 20-sided die is 0.05. So now let's do 100 dice rolls. Okay, getting a bit closer. 1 has a probability of 0.06, 2 has a probability of 0.05, 3 has a probability of 0.1, 4 has a probability of 0.1. So we're still not quite there, but we're getting closer. Let's say we did 100,000. So we're going to do 100,000 rolls. And you can see that our probabilities are already starting to approach, right? We have this one is near 0.05. The probability of 2 is near 0.05. Probability of 3 is getting closer and closer. So what's happening is as our N, our number of dice rolls, gets bigger and bigger and bigger, our empirical probability, which is based on the actual dice rolls, is approaching our classical probability, or sort of the theoretical probability based on the system itself, not on the actual dice rolls. And that's it. That is your quick example of this situation. But we could also take it one step further, and let's make a quick histogram of our dice rolls. And if we look at this, you can see that generally we have a pretty flat histogram, which makes sense because if we have, based on the law of large numbers, we expect that given a large enough sample that we would start to approach that they would equalize out. So just to kind of redo this real quick, let me show you with a smaller roll. So with only rolling 100 20-sided dice, you'll see that there's quite a bit of divergence between how many of each outcome we get. Okay, so that's it. I just wanted to show you a quick example, and this hopefully helps you kind of understand what we meant with the classical probability, the empirical probability, and how the law of large numbers means that the empirical probability, given a large enough size of samples, will actually approach your classical probability.
Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.